finish up with trusses today. We're going to do what's called a space truss. It's not a whole lot different than the planar trusses we were doing. It's just in 3 dimensions, except there's a little bit that changes, a little bit we have to pay attention to. Most of it has to do with the way the object itself is supported. We just have to do a little bit just so we stay in the game of what it is we're trying to do, which for the most part is everything we work on in this class is what's called statically determinate. Statically determinate, that means very simply that we can solve the problem. We will have enough equations for the number of unknowns. You know that from those times where we had the 2 different types of supports, where one of the supports was always on some kind of roller support. Simply because if we had a pin support there, or if we had a pin support and an embedded cantilever type of support, we just couldn't come up with enough equations to solve it. We will add more equations in the spring when we do strength of materials, but we don't have those equations yet. They're not available to us quite yet. So every problem we do here is statically determinate. Because of that, the space trusses are going to need to be supported in a slightly different way than we did with the other ones. So I'll illustrate that as we get into the problem. So we'll start with a nice set of axes. Now, these are true trusses. Remember what the definition of trusses is, even when we were doing the planar trusses?
No, 2 member forces.
A structure made of 2 force members. That means all the ends are pinned, and that's the same thing here. So we'll set it up such that it makes the drawing a little bit difficult. So we'll start here with point A right at the origin. Point B will lie 3 meters out in the x direction, so that's our first member. Is between those 2. I'm going to lay out the structure itself, then we'll talk about the support a little bit, just so you understand what goes on. That has to do with just what we're going to draw at each of the joints as we put the thing together. Point C we'll put right on the z-axis, also 3 meters back. And as most 3-dimensional problems are, this is going to be a little bit difficult to draw, so we just have to be careful. And then point E finishes that square, and that's the base square. And we'll get point D in there in a second, of course. All right, so that's a base, the base of the structure, the space truss that lies in the XZ plane a little bit there. 3 meters back, 3 meters back, 3 meters back. Okay. As you remember, we don't like squares as part of our structure since they're not structurally sound that way. They can collapse. So we're going to run a member across there. Now remember, these are all pin joints, so that these are truly 2 force members. And that's our base. All right, for the rest of the structure, right above the midpoint. So I'll draw that as a reference. And then right up above the midpoint, up at a height of 6 meters, is point D. So this is going to be like a 4-sided pyramid. with a single diagonal across the base. So four-sided pyramid. It's not supported yet. We're going to get to that. Darn it if it didn't happen. I may have to tilt it a little bit just so all of these show. Because otherwise they're laying over each other. Because if I don't tilt it over a little bit, it's going to kind of screw up the perspective some. But if I don't, you can't see this member DB that goes all the way down. Okay, point D is supposed to be directly above that center cross section, even though it doesn't quite look like it. I don't even tilt the axes. If the world's not lining up, just tilt it. There we go. Just to screw you up a little bit. All right, that I just did that so that it's parallel to this vertical line that goes from D down to the very center of the square base. Fair enough? Okay, 3 meters. Oh, and it's 6 meters high. So. Pyramid 6 meters high. So a four-sided pyramid with a single diagonal across the square base, because we can't have squares in these structures. They're not structurally sound. All right, there's our picture. Now for the load, we have two forces. One is parallel to the z-axis in the negative direction. So that would be minus 5 kilonewtons. Okay. Minus just simply because it's pulling in the minus z direction. And then we have a load in the minus j direction. Minus 10 kilonewtons j. So whatever causes those are the two loads. And we want to find the force in all of the members. But first we have to support the thing. We have to make it so it doesn't wobble around. So we could at least keep it from dropping down through the plane by putting some rollers under each of the 4 points. But that's not going to be adequate because then it could the whole thing could shift off of its base and move along. So we're going to have to beef up the supports a little bit as need be. So what we'll do is this. I'll kind of expand it here. So A, if we blow it up here, we've got a member coming down from D. We have this member going over to C. Remember, these are all pinned joints, so we have those two coming in like that. Then we have the one going out to B. So that's the corner at A sort of blown up a little bit. Now its support is going to be a ball and socket at the top and the bottom is going to be firmly held in place. That's going to keep the structure from going anywhere. In fact, point A will not move at all because of that. Point B, if I blow it up too, we've got the member going to A, the member going over to E, we've got the one that goes across to C, and then the one that goes up to D. You can just see why we love these three-dimensional problems. So that's B. Now, B we don't have to hold specifically in place because then that will lock in too much of the structure. We need to have it to have some flexibility. So we'll give it a ball and socket with a little member that we're not going to worry about that also has a ball and socket at its end. So B could move that way in the XZ plane. So that just keeps it from, that restricts it so it can't move in the Y direction. And then we'll also do that in the Z direction. It's like another little two-force member put in there, but we're not going to worry about the forces in that. It's just to keep things from moving around. So this one restricts the Y direction movement. This one restricts Z direction movement. So it can move in the X direction. And then C, notice that as we go through these, we need less and less support because we can't over-constrain the structure at any time. Otherwise, it becomes statically indeterminate. We have to let it have the flexibility it needs to allow us to solve it. So the joint at C then has the member coming down from D, member going out to E, member coming across to B, and then the one going over to A. And that's joint C there then. And this one, we only need a little bit of support just to prevent it from going anywhere in the Y direction. And that'll be sufficient. Now the thing is fully supported. Yep, that's all we need on that one. So I hope your picture looks as pretty as that one does. What?
Point E is just kind of, it's not moving because of the other one.
Yeah. Now point E, we do not need to support. Okay. Now it's sufficiently supported now. The whole structure is. If we didn't have, for example, C in there, the whole thing could rotate around AB and fall down. We want the structure to stay where it is. So what I'm going to try is to put that up on the screen so I can use the board. unfreeze that. Oh, I don't have to do that. Unfreeze. Don't take that. You got it. There we go. Froze that. All right, so we can't see it real well, but you have most of it on your paper, and we'll go through each of the joints one by one now, because the way we analyze the structures is the same way we could have before: method of joints and or method of sections. Whatever you need to do. We need to find the force in all the members. Anybody need the big one, before I erase it so we can start using this space? I'm glad we have it preserved forever, because this is a masterpiece. You have to look at that and wonder why don't we do 3D problems all the time? This is fun. All right, so now we can get to work. So we're going to look for the forces in all of the members.
So when you give us a problem, will we have to come up with the supports ourselves, or will those be
No,
given?
they'll be given.
Okay.
They'll be given. You have to come up with what the supports do, but you will not have to come up with how it supported itself. All right, so ball and socket at each joint, supports, okay, we got it. All right, and we want to find the force in the members. All right, so we got to start somewhere. The place to start is where there are the fewest unknowns, which for the most part means where are the fewest members, which joint has the fewest members in it. If it has 3 or fewer members, then we can solve that joint directly. A has, well, it only has 3 members, but don't forget that's the one that's fully supported. So there's also the support reaction, which is 3 components. But we could do E. We can start with E. So we'll do the best we can here, draw on that. There's E. And remember, we replace the members with the forces they exert on that joint. If we know what they're going to do, we can do that. But it's kind of a mess in these 3D things. So what we'll do is just assume every force is tension. If it comes out to be a negative, then we know it's compression. So that's as good a place to start as any. So we have one force going from E to D. And we'll draw tension, just because it gives us a system. Then we have one force that goes to C, E to C. And then we have the one that comes forward to A. So about the best we can do with it in our drawing. F goes E to A. B. Oh yeah, sorry, B. It looked a little bit like A up there, but it's B. There isn't one that goes from E to B. I mean E to A. So that's E to B. Let's see. FEB, that one's pretty simple because it lies right in one of our ordinal directions. That's whatever its magnitude is, and we've drawn it in the plus z direction, so it'll be plus k. So that one's easy to set up as a vector. All we need to do is solve for the magnitude. FEC, how's that one look? That one lies along the base 2. So as drawn, we're just assuming everything again is in tension, so if we get a negative, it's in compression. What's FEC look like? It's the magnitude, which we're looking for, When it says solve the forces, we're looking for the magnitudes. We'll need to know whether it's tension or compression. What about the direction?
Negative I.
Negative I? Yeah, the move back from E to C is parallel to the x-axis, but in the negative direction. So that'll be negative I. So those two were fairly easy. They were polite enough to lie right on the coordinate directions. And then the FED, that's the one that goes from that corner at E all the way up to the apex of this little pyramid where the forces are applied. And that one we're going to need to do a little bit of work with. Because we're going to need the unit vector in that direction. Remember how to find unit vectors?
So it's a DB, not a B, right?
D, yeah, that shouldn't be a B, that should be a D. Thanks. We're going to find the unit vectors in a particular direction.
Vector of the magnitude.
The geometric vector in the same direction, which we can call E2D, and the order of the letters is important because the unit vector in the other direction is the opposite. So we need to have it in the right direction. So we're going from joint E up to D, and then divide that vector, that geometric vector, just that locates D with respect to E, divided by then the magnitude of that, which we just leave off the vector sign, and that denotes magnitude. All right, to save you a little bit of trouble, I'll just give you that. So we're looking for the magnitude times the unit vector, which is minus 0.236I, because from E up to D is a little bit in the minus I direction. That makes sense? Plus 0.9343J. Yeah, remember we're going up, we're 6 meters above, point D is 6 meters above point E, above the base. And then we're going a little bit in the plus Z direction. In fact, it happens to be the same amount as we did in the I direction. That's by virtue of the base being square and lying right in the coordinate directions. Now, a little bit of convenience for us to speed things up later is these are the same values for the other vectors going up or down from D. So we just need to make sure the sign is right, but we don't need to change any of these numbers. We just need to make sure where they're pointing. So that'll save us a little bit of trouble in a while. Okay, so we've got all the pieces. All right, so we can solve now joint E, because we've got our 4 forces, and we know in each of the coordinate directions the forces will sum to 0. So we've got minus FEC minus 0.236 FED. Doesn't pay to do the left facing equals the right facing kind of thing because it's the 3D problem. It's easier just to add them all up. All the I components, we've only got those 2. So that equals 0. Is that right? think so. FEC is in the minus I. FED is that much in the minus I as well. Okay. And then, not enough to solve it. We've got two unknowns, so we've got to do it in the y direction. Which is, that's in the k, that's in the, there's the only I component we have, or sorry, j component we have. 943 FED is the only j component at joint E. So FED equals 0. Does that make any, well, let's see. Oh, so now what's FEC? Also 0. So we're counting on the z direction to do something for us, or we're out of luck. We've got FEB. The positive, remember, is just because we assumed it was in tension. We'll find out if we were right or not. And the only other K component is FED, and that's positive. 0236. And the Z components must solve to 0, sum to 0. But FED we already know is 0 itself. So FEB is also 0. Does that make any sense? Looking at the structure, that there are no forces in any of the members coming down to joint E.
So
Remember, these are massless.
there's no support, so it's E, right?
There's no support under E.
So it's, yeah.
Yeah, so it's an extraneous feature of the structure. We just don't need it. There's nothing E is doing for us to help hold up the load D. All the load's going to be somewhere else. So you know, as a designer now, then you can take out those three things, unless they're needed for some other region, maybe future purposes, or since it's in space, maybe the space shuttle's going to come dock there or something. Who knows what's going on? But it's at least, because we know that there's no force in those, we call these zero force members, I guess is what we call those. And they conveniently disappear. All right, so that helps. That cleans a bunch of stuff up, at least over on that side of things. So, what joint next? Sometime or other, we do have to do joint D, because that's where the load is, and that's going to really determine the size of everything. So, remember, don't do anything that has more than 4 unknowns. More than 3 unknowns, because we just won't be able to solve it. We'll have to go on to somewhere else anyway.
Hey.
Same as 4. It has 3 going out and then support. You have to do D. It's the only one with 3.
At A, we have 3 members coming in, but don't forget it's fully supported there. So that still is too many unknowns. B out here in front, we just lost the member that goes back to E. It only has 3 members coming in, but it's sort of supported. It doesn't have the full support A does. C has 3 members, but some support, so that's too many unknowns, so we have to do D. D has the 2 known forces. One of the members coming into D is now gone, and so it only has 3 load-bearing members. So we can do D now. So, joint D. We'll start with a free body diagram. Might help if we draw in the coordinate directions, just to help align things as best we can. Just a sketch to help us. Let's see, we have the 10 kilonewton force is down, right? And the 5 kilonewton is out. Those are the two load forces. Maybe it's one load force and those are its components, doesn't matter which. And then we have one force. Remember, we're going to assume tension until we know otherwise. We have the one force coming down to A. So that's FD to A. We have the force coming down to C, which looks almost vertical, but remember that's the nature of the the 3 dimensions. F D to B. And then we have the one that drops back to C. So kind of hard to draw these, just helps a little bit, I guess. Look about right, as best we can do on a 2-dimensional piece of paper. I should have brought some 3-dimensional paper today. Take notes in holograms. And we don't need to draw the force down to E because we already know it's a 0 force member. And so we can sum the forces in the 3 directions and we can get those pieces. Now, remember the components of these vectors all have the same magnitude. It's just we have to make sure we get the sign right. So I'll keep things rolling a little bit here as we do this. So we have minus 0.236 F dA. D to A in the X direction only came out that little bit, the same one the one back at E did. So that'll work. Plus 0.236 F D B. FDB also comes all the way down to 6 meters, but it comes out a little bit in the X direction. Remember, these are only the X components we're doing here. And then DC is 0.236 back. Which makes sense. From D to all those other pieces is the same amount in the X direction. For each of them. Each of those in the X direction goes across half of the pyramid. I guess you could look at it like that. So we could have even pulled out that 236 and made the algebra just a little bit easier, but it's a tough thing to anticipate as we're going through. However, we can anticipate that now. Just like in the X direction, all those components were the same magnitude, same for the Y direction, because from D we come down to the bottom plane for all of those. So we'll just go ahead and pull that term out ahead of time. It's just algebra. And then we'll have FDA plus FDB plus FDC. And remember, FDE is 0, so it's not even a factor anymore. And all that's 0. From D to any of the 3 points is the same magnitude change in the Y direction. So 3 unknowns, we'll need the third equation. Should we do the a moment equation on any of these? Would that make anything easier?
I don't think you're gonna need to.
We can't. Not when we're doing the method of joints, because there is no moment of any of these forces about point. We could do it about the entire structure if maybe we needed to get the support reactions that way, but we'll be able to get them this way because of the forces in each of these. So this comes out to be the common factor 236 FDA plus FDB minus FDC, because in the z direction it goes back a little bit. But then don't forget, in the z direction, we have, oh, I think I forgot something, I did. In the z direction, we have the 5 kilonewton force. In the y direction, we have to add the 10 kilonewton force. So make sure you get the minus 10 on the y direction and the minus 5 on the z direction. Yeah, it's both of those are in the negative direction. And that equals 0. So those of you taking linear algebra are all excited about this. You're probably already firing off the answer. Do you want me to just wait a couple minutes while you do that? Or should I? I'll give it to you. All right, so we have now the 3 forces we can solve from this system. It's not in a linear algebra class, so we won't bother doing it ourselves. 10.6 kilonewtons. It comes out like that, it's positive, so we know that that one's in tension. Because that was our original assumption and we got a positive answer. Plus it kind of makes sense with that force pulling back sideways. FDB, we get minus 5.3 kilonewtons. The minus means that our assumption of tension was wrong, so it's in compression. Now, do not take this to read that negative compression is the same as tension. This C for compression is just confirming the negative sign. Because what we're going to do from now on, we're going to switch it back to its original direction. And the other part, DC. FDC is minus 15.9. So that's the big load bearer there on that one, FDC. Which, yeah, I guess could make sense because that one's getting compression from both the forces. Alan?
B uses FDB as compression with a force pulling it away like that.
Well, don't forget the 10 kilonewton force is pushing down. It's not just the 5 kilonewton force pulling back here. This 10 kilonewton force is also pushing down. That's going to tend to compress dB. The 5 load takes a bit off of it. So that's why that's probably why that is less.
Oh, okay. Because E's not participating.
Yeah, E's, don't forget, E's out of the picture. Okay, so there's joint D. So we just keep doing this. As we do more, we can go to the other joints now, and there's less and less unknown each time. And so let me speed things up a little bit by at least making sure we have the pictures right, because then the rest is a bunch of delicate algebra. So, joint, what next, do you think? One of the ones connected to D, well, they all are, so that's not going to help, but which one now has the fewest unknowns?
Let's see.
Yeah, joint C, don't forget E is out of the picture, so now C has one member coming into it we now know, which is D, DC. We don't know AC, we don't know BC, and we don't know the support reaction there. So we can do C next. Give ourselves just a little bit of a guide here. This is not the original coordinate system, because the origin isn't moving. It's just for guidance for us. So we have FDC coming towards that joint. But now, is FDC compression or tension? We just solved for it. FDC is compression. So I'll draw it as compression just to keep things more accurate now. And then all I need to do is put in the magnitudes as we go. I know it's in compression, I might as well draw it that way. CE, I don't know. CA is right along the axis direction. C2, oh sorry, not DC, we write now CD. Because it's the joint we're starting at. Doesn't matter, we got the direction now anyway. Then we have a joint, then we have this one that's coming diagonally across the base. 2B. FCB. Is that it? Let me recant this one just a little bit. Just give it a little bit of a nudge to the side. Because that's not all. What else is there? F, C, B. And then there's the support. But remember, that was a single support. It'll be in the Y direction only. And so we'll just call that CY. And we'll put it up because that's pretty much what the supports are doing. We're not looking for that one to be in tension or compression because that's not a member. That's a support reaction. Okay, let's see. Don't want to run out of time for everything. We'll do one more of the equation setups here. And then the other ones, more and more stuff is known, gets a lot quicker with them. So, this is 0.707 FCB. That makes sense? Remember, the member that goes from C to B goes diagonally across the base, and the base is a square, so that's a member that goes at 45 degrees. So the 707 makes sense. And it's in the plus X direction, so that makes sense as well. Then in the X direction we have nothing from CA, nothing from CY, a little bit from CD. So we can put that in. Plus, we know its magnitude is 15.9. Its direction is minus 236. That is FCD in the X direction. Because it's going from D, which is a little bit out in front, going a little bit back in the X direction, so that's the minus sign. And I think that's all the pieces. Because none of the others have any X component to them, so that's done and we can solve for FCB. Which comes out to be 5.31. Tension or compression? Tension. Remember all the unknowns, we guess as tension. If they come out to be negative, we know they're compression. So that one's in tension. Remember, that's important. You can always go back to the structure and say, you know what? Maybe I want to change that member out for a cable instead. In the y direction, we've got CY in the positive y direction. CB lies right in the base plane, so it doesn't have any y component. CA has no y component, only CD has a y component to it. And so, where am I? Oh, and I know what that is. I know FCD, in the y direction is minus, yep. Minus, oh, its direction component is the, what did that one come out to be? DC is 15.9, yeah. So its direction component is the 9, is it 4.3?
Yes.
9.43. And it's in the minus direction. And we know what that is because we found it out already before. It happens to be 15. The total now is 15 because it was 15.3, I think. And so now we know that CY equals 15 kilonewtons. We don't say tension or compression on that because that's a support reaction, not a force in the member. And the direction we pick for it is correct because we got a positive. And then we'll do the Z direction for this one, then we'll just get the results for the other two. You can double check them, and then we can analyze the structure as a whole, decide what we want to do with it. In the Z direction, we've got a little bit from CB. FCB, again, the 707. Z direction, there's no Y. CA is entirely in the Z direction. And we assume it's positive. And then there's a little bit of CD in the Z direction, and it should be positive. So its direction component is that one. All right, so that's FCB Z. And we know what FCB is, don't we? Yeah, we know it from up here is 531. So we know that that's a known value. FCD is also known. We found that from the joint before. So that's FCDY. And they all equal 0. Yeah, we have none of the, oh no, we have the load. No, not on C we don't. That was on D. So that equals 0. So the only thing we don't know is CA. We can solve for it. FCA, the only unknown in there, because remember we already know CD and CB. FCA equals 0. Does that make sense from the structure? FCA, that's this little piece here across the back of the square base. The analysis says we don't need that one. We could take it out and the structure would not collapse. Don't forget, CD is there. So if we have the front triangle, ABD, and D is running down to C, it will hold up that triangle. There's nothing AC needs to do. There's nothing, no purpose to it in terms of structure taken as a space truss, and with that load and these all being two force members. So we're eliminating several pieces as we go. All right, so I'll leave for you to check the rest of the results. I'll just give them and we can talk about what we're left with. We started with this four-sided pyramid. We've already gotten rid of several of the members. So we still need to do joint B and joint A. We won't do the whole thing, we're running out of time. Joint B would be the next one. It's the one out in front here. And from that you get results like FBA is one of the unknowns and it comes out to be minus, so we know it's in compression. We get 2.5 kilonewtons. So that's a member that we could not take out of the structure. It's in compression, so we wouldn't want to replace that with a cable. You can if you want that to be your last job with that company. BY, we assume is an upward support reaction, and that gets confirmed. And remember, that was the joint that was doubly supported, so there's a Z reaction as well. I assumed it to be positive, and that's what it comes out to be, in the positive Z direction. So joint A, down in the corner, well, I guess it makes sense. We already took out one member. If you take out any of the other members, we're not going to have much left to support. Oh, I'm sorry, that was joint B. Yeah, joint B, we take out any of those members, that thing's going to start to collapse. And then joint A is the last one, and again, it's just a matter of setting these things up. Lots more is coming known as we go, so they do get easier. You'll find AX equals 0. It's not a necessary support, which makes sense. None of the load was in the X direction, so why would we need any support in the X direction? So that one makes pretty good sense. AY, let's see. Pulling down, that would tend to make A have to push up, but the force 5 is going to try to lift A, so it's a competition between those two. And it turns out the little 5 kilonewton force doing the pulling up is going to be the dominant one. So we actually have to hold point A down in the Y direction. Its tendency is to go up. We have to hold it down. And then AZ, and we're all done, is 2.5 kilonewtons. So we've lightened up the support a little bit. We don't need support at AX. We don't need any of the back triangle that went to E. Some of the other pieces were in tension only. So what happened to BC, the diagonal across? What did we find out for that piece? FBC. Oh, that was in tension. So we could put a cable in there. So now we're left with a much simpler structure. We have the base. We don't need the back part of the base. We have point D up here. We have just that going down to the back corner. And then we need the two triangular pieces out in front. Oh, we don't need this piece right there, do we? Because that was 0. So we come up with just that simple structure. With, of course, the supports that were in there. All right. Not bad. I think you could knock that out on test day, with about 6 or 7 more members in there, just to make it fun.